Hello everyone and welcome again for the next part of that discussion which we had in previous lecture, that is common derivatives of DMs, slope and aspect, and this is part 2. What we are going to discuss in this one is that planar and the other option which is available to us through these softwares. So, basically 2D or 3D Cartesian, or in that sense we have to go for this. So, because in various softwares, like for example in ArcGIS, these methods are different, options are available when you go for calculation, and I will show you a little later about these options and what is the meaning of these options. Though for certain a particular digital elevation model, for if I am say working on a plane area like a part of Indo-Gangetic plain, I employ two different methods, but when I see visually I may not find much difference between two derivatives, means both are slopes calculated through two different options. However, if we go for cell values, again in some cases you may not find much differences. So, depending on our input data, basically these can be different depending on how much variations, basically how much variations which are present within our cells. If cells the elevation values are not varying much, then even if you choose two different options, still you may get almost same results. But if there are large variations in the elevation values of cells of my input digital elevation model, and I apply these if different options, different variants of calculating slopes, I may get different results. So, that is why I mentioned that depending on your input digital elevation model and values present which are having variations in their properties or values. So, if I go for one, the first option is a by default is planar method, which we have also briefly touched in the previous discussion, basically which calculates the or perform is on a projected flat plane and using a 2D Cartesian coordinate system, and that way it calculates basically. So, slope is is a maximum rate of change in the terms of values, and slope value is calculated for the average maximum technique, and this is what is there, that average maximum technique which is calculated, and basically the maximum change in elevation over the distance between the cell and its 8 neighbors. So, that means we are talking about a 3 by 3 matrix or kernel, then identifies the steepest downhill descent from the cell compared to. So, it is a neighborhood analysis basically. Now, another method is geodesic method or 3D Cartesian method. Here it is not assumed as a plane calculation, but it is a 3D. So, that means the calculation is performed in 3D Cartesian coordinate system by considering the shape of the earth as an ellipsoid. And as I have said that if a lot of variations are not present in my input digital elevation model in their values, then no matter which option I go, I may get almost identical results. But if variations are there or I am covering a large area, then the shape of the earth will play very important role, and there I have to take care about this ellipsoid problem or ellipsoid issue. Now, the slope value in this geodesic method of 3D Cartesian method is calculated by measuring the angle between topographic surface and the reference datum, and this reference datum is very important. So, if I take the example of ArcGIS, which is here, which you provide a input raster and of course output raster, when you go for this method which is optional, otherwise by default it is planar, then the two methods as we are discussing are introduced. What the planar calculation will be performed on a projected flat plane, So, your data, which is of course representing the 3-dimensional data, a digital elevation model is projected on a 2D coordinate system, and then it is calculated, and of course this is the default setting in most of the softwares. Now, geodesic is the calculation will be performed in 3D Cartesian coordinate system by considering the shape of the earth as an ellipsoid. And if you want further details, of course those are available. And remember all the time this Z factor, though it is written optional, but in when our digital elevation models are in degree decimal and in the cell values are in meters, we have to take care about this. We have already discussed this, and we will further discuss when I will have demonstration through a software. So, both these methods, planar and geodesic computations, are performed by using again the same 3 by 3 that moving window or kernel. For each neighborhood, that is remaining 8 cells. So, there will 3 in 3 by 3 total number of cells are involved 9, but for if I exclude the center cell, then it is 8 neighbors. For each neighbor, if the processing the center cell, because the calculation is done for center cell, is no data, then output would be no data. This is true in all such calculations where neighborhood calculations is performed. If the center cell is having no data, output is also going to be no data. That is why the concept on no data is very, very important. I also mentioned during early discussions that in older versions or early versions of GIS softwares, and this concept of no data was not there at all, and that gave lot of wrong outputs or wrong calculations because of this. But anyway, that issue has been solved. It is something like Y2K problem. And the computation also requires at least 7 cells neighboring the processing cell which is having valid values, that even if a single cell is having no data, nothing can be done. So, you can also imply if there are fewer than 7 valid cells, the calculation will not. So, only in case of 7 the calculation will be done, but if you are having more no data, of course the output would be the no data. Now, this point I have already discussed, but I will repeat again because this is very, very important again, is that the cells in the outermost rows and columns, that means one thickness equivalent, one cell thickness equivalent row and column, and same with first row and first column, first leftmost column and rightmost column, bottom row and bottom right or bottom row. For that calculation will not be done. So, the cells in the outermost rows and columns of the output cell will be no data, because in that surrounding you do not have on the side, because this is because the boundary of the input data set, for those you do not have enough valid neighbors. You require at least 7. If one cell is bearing no data, is fine, but in the corners or on the margins of your input digital elevation model, it would be more than 7 cells which will not have data, and therefore the calculation is not done. So, your output would be reduced by at least 2 cells by 2 cells on the borders. This you have to remember, one cell thick on all sides. So, it is a kind of border it will create with no data. Now, when we go for planar slope algorithm, the rates of change of delta of the surface in horizontal, that is dz by dx, and in vertical dz by dy directions from the center cell, which will determine the slope. And the basic algorithms which is used for the slope calculation is like this. You can also have slopes in degrees or radians or whatever you want, and slope is commonly measured. Generally, most preferred one is units in degree, and most of these softwares will also have in default in degrees. So, if we have to calculate in degree, this we have already discussed this factor, the 180 by pi. So, this will be required for slope calculation in degree. Now here is the truncated value by 180 degree by pi. Now slope algorithm can also be interpreted as in this form, like a slope bend in degrees, and where you know that rise upon run will be decided based on this expression, and the value of the center cell and its 8 neighbors, like here in this example for each cell the values are calculated and it will be in the both directions, and neighborhood are identified here in this particular example between A to I, which you are seeing A to I, and where E representing the cell for which the slope is being calculated. Always in a 3 by 3 or 5 by 5, 7 by 7, it is the for the center cell the calculation is performed. Now rate of change in x direction for each cell calculated with this following formula. Again there the weights are there. Weights can be also given, that I have been also telling earlier. For each cell in the neighborhood the weights can be given, and that becomes a typical spatial filter if we bring the analogy of digital image processing. So weight 1 and weight 2 are horizontal weighted counts for valid cells, here weight 1 and weight 2 in the above equation, and for instance I may assign some weights here. So for values for my this kernel against C, F and I all have valid values, and they will have weight 1, and that is like this, and I if it no data then it will have something like this, this is 0 is also there. If F is no data then the calculation will be like this, and similar logic will apply to weight 2 also, except neighborhood operators for A, B, A, D and G likewise. So for each cell the calculation is done. The rate of change in y direction for the cell E is calculated with the following. So this becomes complicated, slope calculations become complicated once we go for assigning weight for our this kernel for different cells of my kernel, and that will bring obviously different results. Again it will depend on the input, the variations which are present in the input digital elevation model. Here the weight 3 and weight 4 are the same concept as in computation for the for our in the other x by calculation or x calculation. Now it is for the y scale calculation. Now this rate of change in x direction for the center cell E, which we can also observe in this example, that this is my kernel, the top one, this is my input digital elevation model, and this is my output. So if these values are taken in this substituted in the above equation in the red color, then this is what the calculation will end, and ultimately we get 0.05 for that one in one direction. Now in the y direction, that was for x direction, that for y direction similar calculations will be done, and again that value if I substitute these values I get a minus 3.8. So for taking all this together x and y directions, the slope of the center cell is calculated using following formula, that now I am bringing and x direction, I am bringing y direction, same concept rise upon sun. So dz by dx we have calculated 0.05, and where dz by dy in the earlier slide we have seen is minus 3.8. Of course it is a square, so then the negative values will disappear and it is 3.8, that is slope in degree which will be multiplied by this factor, and then finally we get this one is 75 degree. Now these are not represented in our results in fraction because for that kind of accuracy for topography, and topographic slope is not really required. So, a rounded figure is represented for degrees, and if somebody is very keen, and definitely some modifications can be done, so that you can get even the after decimal places. So, 75 degree. So, we started with this center cell E, and the center cell value initially was 30 degree in an input digital elevation model, but through this neighborhood analysis for planar x y direction slope calculation, ultimately we get for the center cell value the slope is 75 degree compared to what. So, it is basically a neighborhood analysis. Now, when we go for the second option, that is geodesic method, a 2D Cartesian 3D Cartesian system, then this geodetic method, as you know, measures the slope in geocentric 3D coordinate system. Things may become little complicated in that sense, because now we are bringing an ellipsoid which is earth centered, earth fixed ECEF coordinate system. This concept is also valid in case of these navigation systems like GPS or Vaidu or NAVIC of India or Galileo or GLONASS. There also different ellipsoids are used. Not all navigation systems are using the same ellipsoid, they are using different concept. But GPS, like for example, uses this ECF concept, that is earth centered, earth fixed coordinate system, because there also the 3D calculation, the 3D Cartesian system, coordinate system is required. So, for computation of results will not be affected by how the data set is projected. So, from that point of view, there in case of 2D Cartesian or planar calculations, the data is first projected in 2D plane and then calculation is done. Here no matter whatever the data is projected, it will do the calculation. It will use the Z units of the input raster, that is the cell values, if they are defined by spatial reference. That means they are georeference, and generally we are having. So, if the spatial reference of the input does not define the Z units, one has to be provide that parameter, that Z unit parameter. So, in the geodesic method, which will produce a more accurate slope than planar method. Again I will tell you that important point is how variations exist in a input digital elevation model. If values of elevations are not varying much, then you may get almost the same results, though on the cell basis if you do the comparison or create a subtracted slope map having two different options, you may get some results. Otherwise visually there are not much difference. However, if variations, elevation values variations are much high within a file, you may get a completely different results. One, and also it will matter how big area is being represented, though the calculation is done only by using a 3 by 3 matrix. So, this geodesic method produces a major accurate slope compared to planar method. Now, this very briefly I will touch about this geodesic coordinate transformation, that is earth centered, earth fixed one, where though here because earth is not perfect spheroid, so here it is a little exaggerated thing for the polar regions. Just to explain that the surface is transformed from input coordinate system into a 3D geocentric coordinate system, that is ECEF, earth centered earth fixed coordinate system. So, whatever the input which is coming through the 2D will go in the 3D. So, ECEF coordinate system is a 3D right handed Cartesian coordinate system, because coming from north, east and likewise. So, right handed, center of the earth as origin, where any location is represented by x, y and z coordinate system. So, in 2D you will have only x, y, but here also a z coordinate system. In GPS or GNSS you get the estimation of the height, that is why they are also following the similar geodesic Cartesian coordinate system or 3D this thing ECEF. And like here for a target location T, which is shown here x1, y1 and z1, and then which is expressed in the geocentric coordinate system, and then you get better results. Now in this geodesic computation for x, y, z coordinates is calculated based on its geodesic coordinate, that is latitude which is represented by phi, longitude, lambda and height h. So all three are there. Now as I have mentioned that more complications will come once you go for more accurate estimations of slopes. Still I am using word estimation because after all digital elevation model is a model. It is not a complete true one-to-one scale thing. The real one is on the ground only. So in a model you are assuming few things here, and therefore the same thing also happens in once we go for height calculations or altitude estimations by employing these GNSS systems, and there we also encounter this problem. So similar kind of problem will also come about the height, above mean sea level or whatever. So like here this is the ellipsoid surface which you are seeing like this, and what basically you are calculating this the T which we have just discussed in the previous figure, this T x1, y1 and z1 is basically what we are getting above the topographic surface. But whether that height is perpendicular or this is our tangent plane which is just touching this ellipsoid surface, so whether it is perpendicular to that or not. So again if it is coming from the earth center, then definitely it would be the ellipsoid normal, otherwise not. So the variations may come in our, that is why in GNSS you get the variations. You expect something but you may not get the accurate elevation value. Though for XY, that is in 2D system, that issue is not there. So generally the coordinates in like GNSS systems you get very accurately. So it's almost the same issue is here, that we are representing a topographic surface, whether these my for which I want to know the slope, my input x, y and z, whether they are having this kind of relationship or not. So if coordinate system of input surface raster is a projected coordinate system, the raster is first reprojected to a geographic coordinate system, that is GCS, where each location has a geodesic coordinate and then transformed to the ECF coordinate. Lot of calculations will be required to get an idea or to get a slope map through this geodesic computation. So if you choose this, obviously on even a small file it may take some time and it may require some extra inputs from. And as height is z, that is the z value here, the z value is the ellipsoid height above this surface, whereas we say above mean sea level. So this reference becomes our ellipsoid, though that can also be adjusted above mean sea level. But again that is also depend on the model, that what is our based on our gravity surveys of the earth, the model is there, that is the geoid, not ellipsoid but the geoid, and based on that then heights are influenced or estimated. So this to transform our ECEF coordinate system to a geodetic coordinate system, that is in terms of latitude, longitude and height, and the following formulae can be employed. X for x like this, and for y is like this, and of course for z is like this. So where, as you know, that these are the further details are there for latitude, longitude and heights. You have also seen in case of ellipsoid that A represents the major axis of the ellipsoid, and of course the B then represent the minor axis of ellipsoid, because Unfortunately, Earth is not perfect spheroid, and therefore these complications come, and we have to while going for more accurate and accurate slope calculations in current discussion, then we have to take care about this. So, ellipsoidal height h is in meters above the formula. Through these above formula, your input rasters z unit is specified. If in any other unit, then internally transform to meters, because it has to be converted, then only you can do. So, if we go for this option, that is geodesic slope calculation, is this angle formed between the topographic surface and ellipsoid surface, and any surface parallel to the ellipsoid surface will have of course slope equal to 0, that is the flat, and the calculate slope for each location, again employing 3 by 3 cell kernel, and also fitted around each processing cell using a LMS or LSM, that is least square method. And the best fit in this LSM minimizes the sum of squared differences, that is dzi, between the actual z value and fitted z value. And this is what we see here, that the plane is represented here with the z equal to ax b by n plus c. For each cell, the dz is the difference between the actual z value and the fitted z value, because instead of in 2D, now we are talking in 3D. So, that much care is required, and the best fitted plane is expressed like this, which minimized the variance. After this plane is fitted, a surface normal is calculated for each cell or at the cell location. Surface normal, which is a tangent and going like this is represented here with blue lines. Now, surface normal is this one, when it is again it is taken as above this level or topographic surface, and then it is done. So, after plane is fitted, a surface normal is calculated at each cell location, and in the same location an ellipsoid normal perpendicular to the tangent plane of the ellipsoid surface is also calculated. So, here one normal, ellipsoidal normal, here another normal, which is surface normal. So, all these have to be calculated. Now, the slope in degrees is calculated from the angle between the ellipsoid normal and the surface and the topographic surface normal is this one, which is the beta here. So, this angle alpha is the same angle as beta pursuant to law of congruent geometry. And to calculate the slope in percentage rise, of course, the formula would be little different. You have to multiply by 100 to get that one. Now, they for 3 examples are shown for different types of terrains of USA, and with the 3 examples and 2 different methods, that is Horn method and this Fleming and Hofer method. And for what we see, when elevation range is, it is showing like this, slope maximum is this, and relative value is this. Similarly, for these the same different regions, and the values are varying, slope of course will vary, and the STD are varying. So, now if we compare this slope maximum with this slope maximum, obviously earlier I also discussed that in the previous lecture that the results are going to be little different. Similarly, here that this deviation, so relative value here is this, it is also having little different variations. So, because the terrain, the purpose here to show this comparison, because the terrain is different, though methods might be same, but the results would be different, because our algorithms which are being employed are completely different. If we employ this diagonal rater and a simple method, and then again these results are huge difference here 8.4, this is 13.36, and standard deviations relative values again 3.09 and 5.02. So, different for different terrains. This is the point which I have been mentioning. If lot of variations are present, results are going to be different. If less variations are present, results are going to be different, no matter what method you employ. And last one, the slope tool, which is available in ArcGIS and as a special in the spatial analysis extension or toolbox, and there it may give you different calculations. So with this I end this discussion by repeating only one important thing is about, and no matter whichever the method you employ, you first take care about the Z factor. If you do not take Z factor care and you just go as default, which is 1, that means the system will assume that your XY scale and Z scale are same. If in your input digital elevation model these are not same, then you should convert one to another. And for India we have already average value has been calculated, and that is 0.5 times 0.89. If you provide that Z factor, you may get better results than going for 1, which is obviously will give bad result. Visually you may not see much difference, but when you see based on individual cells or zoom it and then compare it, definitely you would get different results. Similarly, if you employ for different methods like horn method, Jevons-Garvan or Thorne method or simple slope tools or any other tool, the jitter, diagonal jitter, you will get definitely different results. That's because the algorithm based on the algorithms which they are using are little different. So with this I end this discussion. Thank you very much.